discuss some important parts. These are the important things from our module 4. Okay, so the first important thing that I'm going to cover would be the interpret driven IO. Okay, so the first important thing would be the interpret driven IO. So let's start that. I don't know why the page is not loading. Okay, so we are talking about interpret driven IO, and we have to understand the first thing is how the interpret driven. So this is what I'm going to discuss. This is very important thing, the working of the interpret driven IO. Okay, this is the first important thing that we are going to discuss right now. So from the IO module's point of view, we are going to discuss the interpret driven IO's working. That is, what happens is that first what happens, the IO module would receive the read command from the processor. So first it is receiving the command. Now you have to understand that read command would involve what? That read command would also involve the address from which you have to read, the address of the device from which you have to read, and where I have to store that data. All this would be included in that read command itself. Okay, now the next thing that would be there in the in interpret driven IO is that after, now what happens, the IO module has that command. Okay, now what happened is that after CPU would give that command, what happened, the CPU would go. It does not wait there. It would go and it will go and do some other things. So what happens in the IO module, CPU's command that the CPU gives, that is the read command, is now there in the IO module, and CPU now what happened, leaves and do some other work there. Now IO module, what it will do is that it would proceed here, then proceeds to read the data in from an associated peripheral. So what it is going to do is that the IO module is now working independently and it will communicate with its connected. Now IO module is connected with some peripheral device. It will connect it will communicate with this physical device, and from where you have to take the data, it will collect that data. Okay, and the CPU at that time, what it is doing is that it is doing some other instruction. So here if you see IO module, which is what it is doing is that it will be fetch the data from the hardware and will buffer that data in its data register. Now the data is almost ready. At that time the CPU would doing program A, it would run program B, it would run program C, it would run. These are the things that the CPU would do at that time. Now once data are in the modules, now what happened, after fetching the data from the hardware, the IO module would place this data in the IO module will place that data in the data register, buffer it and place it in the data register. And the module, now what happens, now it happens is that the IO module's internal data register, it will store that data. Now the module would send interpret signal, that is interpret request signal, that is IRQ, on the control line bus. So there is interpret control line. Okay, that is an interpret control line. In that interpret control line, to this interpret request signal it would send, and CPU would detect the signal only at the current. That means if it is executing, let us say program C, at the end of that instruction, current instruction, only it will detect this signal. So now what happened, the data is ready in the data register, so it would send interpret request signal to the interpret request interpret control bus. Now what happened, the CPU would detect that signal from the bus at the end of its current instruction. Then the module then waits until the data are requested by the processor. Now it would send the interpret signal and it would sit there. Then the IO module would hold the data in the register and it would wait there patiently. It would wait there. It doesn't send data directly to the CPU until it requests. When it sends the interpret, now what happens is that the IO module is now waiting for CPU to request that data. When CPU requests, when the CPU receives the interpret signal, it would request. Only after the CPU sends the request signals, then only the data it will give to the CPU. Okay, if this is not happened, if the waiting doesn't happen, means it is basically used, or this mechanism is used to ensure data isn't lost or corrupted. Okay, so when the request is made placed, what happened is that the module will then place that data. Now on the database it will place that data, so that now the CPU can read that. So IO module put the data on the data bus and the CPU would pick that, and the IO module would again get reset. That is, it would be ready for doing the next operation. This is how it works in the IO module's point of view. So in the IO module's point of view, what happened is that the IO module would receive that read command. That read command includes from where it has to read that device and where you have to store all those information are present in the read command, that it would give to the processor, and the CPU would go and do the other task. Now while the CPU is doing other tasks, it would be fetching the data from the given device in which it is connected to, and it would also basically buffer it in the register. Now finally the data would be stored in the data register. The operation is completed. So what happened is that the IO module will send interpret request signal through this interpret control line. So that control line is there. So the CPU would detect that signal, and what it will do at the end of the current instruction only, it will detect that signal. So it will wait, the IO module will wait until the CPU is requesting for that data. When it requests only, it would give that data to ensure data is not lost or corrupted. Now, when the request is made, that data, the IO module will put it in the data bus and the CPU would pick that data. Now the IO module is reset and it is now ready for the next operation. Now, how this works in the processor's point of view, let us understand how this works in the processor's point of view. In the processor point of view, these are the steps. The processor would give this read command, then it goes off and does something else. That is, CPU sends the read command to the IO module, and CPU would basically goes off and it will do some other task. It will immediately run program A, handle some calculation. CPU is productive at the time, it is not idle. So by that time you can say the CPU is doing some other important thing. Okay, now at the end of each instruction cycle, what happened is that the processor would check for the interpret. So here what happens is that at the end of each of the instruction cycle, so when it is executing one instruction means it would fetch that instruction, it could decode that instruction, it could execute that instruction. After that instruction is finished execution, then only it will check if there is any pending interpret it has to handle. If there is no pending interpret, then it will go and do another, fetch another instruction. If there is interpret, then it would handles that. So what happens in the CPU is that since it is doing some other task, at the end of one instruction, that means one instruction ending is what? Fetching part is finished, decoding part is finished, executing part is finished. Only after finishing the executing part only, it will see whether CPU has any pending request or not. If there is any pending request, then the CPU would go and handle that. Otherwise, it would go and do what is that? It would go and do the next instruction. Now what happens when the interpret from the IO module occurs, the processor would save the current instruction states, that is the current program counter, the CPU registers, the status or flag registers, stack pointer, all of these things it will save of the current program. Then only it will handles the interpret, that is when it finds that okay, there is a pending interpret, so it was executing on current program, it will save its program counter for remembering where you have to return, and the CPU registers preserve all the values that is there in that register, and status or flag, that the conditions code, that also it would preserve. Stack pointer maintains the memory stack position, the stack pointer, the CPU registers, the condition codes like the status or flag, program counter, all this value it will save of the current instruction, right? And it will go on handling the interpret. So if interpret occur, the PC, the registers value, the flag value and all would be saved. Then only the CPU would jump to interpret service routine. So ISR means that interpret service routine. Handling of this interpret, that steps are known as interpret service routine. Okay, so in the processor's point of view, these things are basically saved: the program counter, CPU register, stack pointer, and the condition codes like status or flag registers. In this case, what happened? The processor would read the word of data from the IO module and it will store it in the memory. So the CPU now what is going to do is it would execute the interpret service routine. It is a special code that is going to read the data word from the IO module's data register, transfer it to the appropriate memory location and acknowledges the interpret. So the IO module know it is done. Now after it is transfers it to a memory location. After it done to that, it will acknowledge the interpret. So the IO module now it is done. ISR code means read data from the IO's data register, and what we are going to do, we are going to write it to the memory address. That data, this is the data. So we are going to read data from the IO module's data register, and we are storing it in AL. Now that data we have to store it into a memory address. This is interpret handling routine code. So it is a piece of code that the CPU executes, that it would read a data word from the IO module's data register, that is IO module's data register INAL, then data register, IO's data register. So IO's data register means from here we will read the data and move to write it some address, one memory address we will write. To there I want to write it. So that means this data in the AL I will write it in the memory address, and this is the interpret handling is completed here. So it then stores the context of the program it was working on, and it is so CPU would now restores the PC, the registers, the flag, right, these things, CPU, registers, flags, stack pointer and all, it would restore them, and it will continue executing the other program. So interpreter program has no idea it was ever posted. So in this way the interpreter program would have no idea whether it has been post or not. So this is what basically happens. So in the processor's point of view, you have to understand that the processor would send read command, and it will go on executing the other program. It will turn off and go and execute the other program. So at the end of each of the program instruction, it will see if there is any pending interpret it has to handle. Then after that only it would go and store all of these things in the its then it will do the ISR code. Then it will restore and do what it was doing before.